do the wrong problem.
Vinny is 5,615.
No, it is 16,000.
Oh, I did it wrong?
You did it
No,
wrong.
what's 16,000?
Hey, did I do the wrong problems?
3.2?
It is 16,000.
Three.
Okay,
No way.
so is there still some parts of the homework people want to look at? Clearly.
Yeah, can you go through A through F?
That is 1.3.
A through F?
A through F.
We probably won't go through all of A through F.
So definitely D.
Definitely D.
That's the one that I sent to you and you just destroyed.
Let's see.
So,
Sorry, what page is that? My bookmark is on chapter 4. 93. Thank you.
92.
The one.
So we want to look at,
Guy's hard to.
okay, so we've got a 18-foot beam.
Yeah,
We've got a 12 kip load.
which is just 12,000 pounds, right?
Yep.
Okay.
Yeah, I
Uh-oh.
had one of them too, and then you
Hey.
never called me back.
That guy from the first semester, the engineer, that Hulk over there, he was beginning the French. And he put that in the dock.
Oh yeah, you can't even
Really? That's competition.
He's first
turn it
semester.
in.
Yeah, but he's also a guy like Brad Hartman.
Bad. Like you can't turn it in.
Yeah, I have it just shut down at
Oh, you
10.
just
We'll
shut it
adjust
down.
it.
Okay.
Once we talk through a couple problems, we'll figure out how much time people need. If we should extend it till 10 o'clock tomorrow, midnight tomorrow, whatever it is, and then I'll reopen
I
it
just
for
make
everybody.
sure you're aware.
Yep. Oh, thank you for pointing out.
So it's 200 pounds a foot.
Yep. 200 pounds per foot. Okay, and this distance is 10 feet.
10 feet and then 8.
And this distance is 8 feet.
Yes.
Okay. So, what is the first step that you need to do?
Find the moment around R1.
Yep. Okay. And John's jumping ahead, but we're determining equilibrium, right? We want to
Yeah.
make sure that we determine our static equilibrium,
Mm-hmm.
right? But yes, John, you're right in that our first step, though, too, in order to help us determine
R1 and
R1 and
See, like,
R2,
I don't know why.
we want to make sure that the
0.5.
sum of our forces in the y direction are also equals 0,
Because of the.
That'd just be the distance, not the actual weight.
right?
The weight still is across the whole thing. 0.
Okay, so what forces are acting in the y direction?
R1, R2, and 12,000.
200 's not?
Pounds per feet.
Oh, and the 200 pounds per feet. 3,600.
Do you want us to show that?
No, it was times 9.
I need to know how to answer these too, like just what the hell you want for the answers.
Sure. I guess if I don't see this on your homework, I'm not necessarily going to take points off for you.
I didn't do that.
But keep in mind that if you don't have this on here, do you have all your appropriate bookkeeping? If you don't have all your appropriate bookkeeping, you may lose something in the shuffle. Okay, so it may cause you to lose points, but if I don't see this, I'm not going to dock you points. No. Okay? And we've done, and I guess I should say before we move on, we've done this type of problem enough now that we know that we can't solve this, right?
Yeah.
One equation with two unknowns.
And X would just be 0, right?
Sorry, say that again.
The-
Why?
that is
Oh,
Y.
some of our forces in the X direction, yes. Do we have anything acting in the X direction
No.
in this particular instance? We don't, right? I mean, we have, if we're pinned here, we would have a horizontal component, it would just equal 0, okay? So yes, we're good there. And so where would you like to look? Would you like to look about the
R1.
reaction at 1?
R1.
Yeah.
Okay. So the moment about R1, what does it equal? What forces are acting on it?
12,000.
Okay,
10 feet
12,000 pounds, 10 feet away,
and
Okay.
3,600 at 9.
3,600 at 9. Yep. Does everybody see what John did?
No.
Okay.
Figure that out.
John, what did you do?
I gotta give credit for Terry to this, but you,
Okay.
You just do 18 times 200 to figure out how much weight there is total.
Yep. Our uniformly distributed load is applying force of 200 pounds per foot across the entire span.
And you divide it
Okay?
by
So
2.
you multiply it by 18 feet,
Thanks, Benny.
that gives you the magnitude of the load. Okay? 3,600. And Marshall, what did you say for determining the location?
You divide it by 0.5. Or
time.
times it by 0.5, I mean.
You multiply the entire span,
Yeah,
right?
the
Because
whole
in this
18
case,
feet.
it's acting on the entire span. What would we do if it was only going to 12 feet?
6 feet. Do 6 feet.
Place it at 6 feet, right? And you'd multiply your 200 pounds per foot times, careful, by 12, right?
So it's going the way up.
You need to determine the magnitude, you multiply the pounds per foot by the distance it's acting over the entire beam, okay? Everyone follow that?
Yeah.
Good. Okay, so,
Here's what I,
go ahead.
so when we've solved for the reactions before, we would take 12,000 pounds times 8 and then divide it by 18.
We would take 12,000 pounds. Yep, hold on, we're not there yet, right? We're still taking our forces into account. Okay?
But we just multiplied it by 10. So we're going the opposite way. Like when we work through these problems in assignment 2, the first time the load hit, we take that with the remaining feet and multiply them together.
If we were looking at it about R2.
That's how it is in the book too. If we're looking at R1, that has to go from the other side.
Yeah. You come back from R2.
Yeah.
And then
So
you come up
once you
with
divide it,
R1.
you'll get your, you know what I mean? That'll get you, and then you divide it and you'll get all your answers. But the way it's written out, you know, it'd be. It's
I guess
not-
I'd have to go back and look at an example. I mean, that's not how the math will work. I mean, just think about it. If you're looking at it about this point, right? Here's where we're tending to cause rotation. Is this force 8 feet away from this point, or is it 10 feet away from this point?
I get that.
Okay.
I get why you're doing it. But when I went back and looked through everything, I was like, that's not what we did.
Interesting.
Yeah, I can
Yeah.
show you the damn assignment.
Okay. Well, I'll look back at it. Okay, so we've resolved our uniformly distributed load into a force of magnitude 3,600 feet that is 9 feet away from the reaction. Okay? Do we need to take R1 into account?
No, because there's no, it's going through that.
It's acting through the point, right? Okay, so it's a distance of 0 feet away, so it's not creating any rotation.
But then you have R2 at, negative R2 at 18 feet.
Not how I have it in my notes.
Okay? Does that make sense to everybody? So if we need this to equal 0, we can say that 18 R2 will equal 120,000 pound-feet plus, let's see, that'd be 36,000. 4 times 9 is 3,600. So it's 32. $32,400 pound-feet, is that correct?
Barely.
152.
15247, yeah.
Okay? So R2 will equal 152,400 pound-feet divided by 18 feet.
8,467.
Okay?
So would you? So my immediate reaction would be like, okay, we're gonna take the 12,000 and the 3,600 and add that together minus the R2 and you'll get R1.
Yep.
So,
Equal,
You're right.
oh, what is that? Oh, yes, sorry.
But it's not
That
right.
shouldn't be positive, right? These should be
Okay, right.
negatives. Right? Because if we're saying that these are positive,
15,000.
these values have to be negative, correct?
Yeah.
So it equals 15,600 pounds minus 8467 pounds. So that's what, 7133?
yeah,
Yes, sir.
close enough.
I was right on one of them.
Okay?
You should have been right on the other.
No, I wasn't. No, I wasn't.
Dude, it's when I did my diagrams, when I knew it was off. So I did the
Sure.
12,000 and I went way below my other reaction, that's when I, you know, something,
Yep.
something's not jacked.
So
R1 equals.
where is our greatest shear going to occur?
At R2.
At R2, right? It's our reaction with the greatest magnitude. Okay? So are we ready to try the shear diagram?
Yeah, let's do it.
See it?
That's easy.
Okay? So if we go an infinitesimally small distance to the right of R1, okay, we can't measure it, but we're feeling the effects of R1. What is the magnitude of our shear?
1,133.
7,133 pounds. If we go 1 foot to the right, what will our shear be?
7,000 minus.
7,033.
6,933.
6933, right? Because 200 pounds per foot,
Chill out,
right? So we should be dropping 200 pounds per foot until what point?
10 feet.
For 10 feet, right?
And then we go.
What's our value? Just to the left,
5133.
5133, yep. And then when we get just to the right of the 12,000 pound force,
We drop to whatever day.
Negative 6,867.
okay? Now if we go 2 more feet, what happens?
We continue to drop.
400 more
400
pounds.
feet.
We drop 400 pounds, right?
Pounds.
Okay? And we continue doing that until we reach,
Negative 847,466.
Yeah, that was so far off on this.
I was close. I got one right, but not. R2 correct.
I'm just gonna roll the dice on the first thing and see what this is. So, now, can you do me just a favor here?
yep,
How do you want your answer? So we just do R1 equals this, R2 equals this,
Maximum value shear.
that's it. We don't have to write shit. Alright, cool.
you need your shear diagram, denote where this where is this,
Like 10 feet or,
Yep.
it's right 10 feet there, okay.
and what is Vmax,
So, that's what I was gonna do.
okay? So, yeah, if you need to solve your reactions, include the magnitude of your reactions. You need your diagram, you need your entire diagram, okay? Denote where it crosses 0, and identify what your maximum shear is. Yes, sir?
So when we were doing shear, you mentioned on Tuesday, shear is right before and right after the point, but the other thing is the
So
actual
that's
point.
bending though.
Bending,
Bending?
we're taking account the point.
That's where I started getting mixed up. I was like,
Okay.
if I'm at 10 feet, do I count to 12,000? Or do I gotta go past it? That's bending, ain't it?
It's shear.
Think about what bending means. What is bending doing?
Military gets special lift.
Bending's trying to rotate, right? Okay? So at this point, if we're looking at this beam and we're trying to figure out how the forces acting on this beam are trying to bend it, is this force trying to bend this beam at this location?
Yes.
Is it trying to bend it? It's trying to shear it, right? The shear will cause this portion of the beam to try and bend.
But not at that.
It will
exact
try and
location.
cause this portion of the beam to bend, but it will not try to bend the beam at this point.
So does a beam have both going on at the same time?
Correct, yes, absolutely.
Okay, so it's not two separate things. It's shear is like the center of the bend.
Shear is the center of the bend.
Bend's the most, got the most.
I can't show you. I'll show you.
Kind of. There are two different types of
Right.
actions exerted on the beam by the forces.
Let's not get ahead of ourselves.
No, this is what we're talking about. We're
I
talking
know,
about shear bending.
I don't wanna try to,
Wrap your head around bending when we're talking about shear.
yeah, it totally threw me off trying to do this and then like the bending started getting like warping its way into my head and
Sure.
So bending, we are taking,
No,
stop saying bending, bending.
we're not talking about bending right now.
There we go. So that'll help for note wise.
But John, to go back to your question, shear takes place as soon as the force starts acting on the beam.
Ooh.
Okay? So that's why we can say if we're just to the left of it, right,
okay,
it's not acting on the beam. If we're moving left to right. As soon as we get just to the right of that force, now it's acting in shear. Okay? As we're moving through and looking at bending, when we're at that point, it's not doing any sort of bending. As soon as we get 1 inch away, it's now bending. Okay? Does that help?
nope.
Okay.
Skip class, backward bending.
So on, back to this assignment real quick. When there's the weight that goes across the beam, that's a 200 pound
The
per foot.
uniformly distributed load.
Yeah, when it's not, do you make, like, when we were doing the other ones, you just say, okay, for this section, it's 500 pound per feet, let's say for 5 feet, right?
Yep.
So we'd take a 2,500 and put it at 2.5 feet
Yep.
and make it a load, right?
Yep.
And then just use that to solve.
Yep.
Okay. It all makes so much sense when I'm sitting in here, Ben.
That's the point, isn't it?
Yeah, and then when we get home, completely level.
Yourself, but it's like, yeah, no,
Okay, all right, I think I can do the next two.
I don't.
I'm gonna try it, just, you know, if we do it all, and we do all the work, we shouldn't lose points for being wrong.
Oh, is that how it is?
Yeah.
Okay.
Because it's a new,
Is that,
it's 2018, bro.
Is that how we should do it in the industry too?
Yeah,
Like, hey, look, I
it's
mean, we
effort.
did the calculations.
So look at the effort
We
you
were able
put
to
out.
build the bridge, and the bridge fell, but we tried.
If I was gonna be
I
an
mean, we
engineer,
tried.
yeah, if I was gonna be an engineer, yeah, that'd be cool. But
I mean,
I'm not.
like,
Do
what
you wanna
what
look
if
at it
all my
out?
calculations were correct, just my numbers were wrong, but like, that made sense? Just saying.
But if your number was wrong,
35W.
how could everything else?
It happened.
Okay, do you want to look at A or B?
No, A and B are like.
So those I did without even doing like, doing math, you can just look at them and know how it goes.
Okay. Do you want to look at something else then?
E or F.
F kinda, but
That would be absolutely.
yeah, it's F's got some bite to it.
200 feet, there, there.
Okay, 93 F.
Oh my god, this pencil blows.
I think you will.
What's gonna happen then?
Hey,
It'll be a class, guys.
Terry, I'm about to take another pencil.
Okay, so we have a 18-foot beam again.
Your notes were there, good help.
2,000 pounds is right in the middle.
Pounds at 9 foot. Okay, and then we have 1,000 pounds 3 foot away.
Does it give us the,
And then we have oops.
the 100?
Oh, terrible scale, sorry.
So 1,000 pounds at 3.
Okay,
What was the, it's 300 pounds. So X is still 0.
X forces, still 0, right?
Yeah.
Nothing's working in the X direction, so we're good there. Y direction,
Okay, so it'd be
R1,
R1 plus R, yeah. Plus 2,000 plus 1, or just, you want to write 3,000, or it doesn't matter? Do you separate those?
I would separate them,
Or minus?
just because from a bookkeeping standpoint, you can run along here and you can say, I've got R1, I've got R2, I got my 2,000 pounds, I got my 1,000 pounds. You just go through and check all your boxes,
Okay.
right? That would be my recommendation. Okay?
minus 600.
What was that of 100?
Okay, so John is saying
Minus 3,600.
300 times 12 feet, yep. Okay, everyone agree with all of that?
So 12 feet times.
Are we missing anything?
No, I don't think so.
We've got both our reactions, right?
Our-
We've got both of our point loads, and we've taken into account both of the uniformly distributed loads. So we're good to go,
Okay.
okay? But again, we also know that we can't solve this. We have 2 unknowns, but only 1 equation. So if we can determine that our moments equal 0, we should be able to have R1 or R2 fall right out, okay? So, which point would you like to look at?
Let's just stick with R1, that way I have the
Stick
same
with R1?
process going, yeah.
Yep. So let's look at our 2,000 pound first.
So that would be 2,000 times 9?
2,000
9 to the left
pounds
though, right?
times 9 feet, right?
Yeah.
Is this causing a clockwise rotation, or is it causing a counterclockwise rotation? It's causing clockwise, right? So it's going to be positive. Okay?
Right.
Let's look at our 1,000 pound force. What do we have there?
1,000 pounds at
15.
Times 15 feet.
Terrible one.
And what about its sense? Is it causing clockwise rotation?
Yeah.
Clockwise rotation, right? Okay. Okay, how about your uniformly distributed loads?
600 at 3 feet.
600 pounds at 3 feet. Okay, so John took that he's got 100 pounds per foot over 6 feet. So he's got a magnitude of 600 pounds. He knows that he's got a 6 foot distance. He's dividing it by 2. Okay, does everybody see that? Everybody following along?
So it'd be 600 times 3.
600 pounds times 3 feet. Yep. If you want to write it out,
600
it's going to be 100 pounds per foot times 6 feet times 6 feet over 2, right? So here is your force. Here is your distance, right?
Yeah.
Remember that the equation for moments is force times distance. Okay? So if we multiply our distributed load, loads per feet, times its distance, our feet are going to cancel, giving us a pounds value, which is what we like to see
600.
in our load, right? 6 feet divided by 2. So we're moving it to the halfway point. That's going to give us our distance.
So,
Okay? Now regarding this force, is this going to be acting in a clockwise direction or counterclockwise? It's going to be clockwise, right?
What do I have to do?
well, which would be a 6.
Now what about our 300 pound per foot force?
It would be,
36 times 6. 3600 times 6.
600 times 6.
no, times 6. Or would you still
Uh-oh.
add the beginning 6?
I want to say 12,
Why, Kurt, why do you want to say 12?
because it's at the middle of that load.
It's going to take place at the middle of this portion of distribution, correct? So it would be 6 feet here. How far is this point from R1?
12 feet.
12 feet, okay?
So you do add the first 6 feet.
Yep, because remember, we're looking about R1. Now, you're correct in your initial assessment. The location of the magnitude with respect to the overall 12 feet that is taking place, yes, that is where it's going to be. But we have to remember where we're conducting our analysis. At this point, we're conducting our analysis around R1. Okay, so we have to measure this distance. So it would be 12 feet. Okay?
What was that, 18 times?
So how that would look, if you want to write everything out, 300 pounds per foot times 12 foot plus 6 plus 12 feet over 2, right? Where this 6 foot is getting us from here to here, right? And then our 12 foot divided by 2 foot is saying, over this entire span that this force is being acted on, I'm putting it at its midpoint.
Okay.
Okay?
Delete.
Divided by 18.
Oh, yeah.
What about our reaction?
So
R2.
times 18,
R2 times 18. Is it acting clockwise
negative.
or it's acting counterclockwise, right?
So 4, 3, 3, 4.
Yeah. You got 700?
78,000. Yeah.
Which one is it though?
R2.
Yeah, I was mixing it. That's where, you know, the whole time I'm mixing for R1.
Yeah.
And then all of a sudden I end with R2.
To get R2. Yeah.
$33, 76.
78,000.
78,000?
Yeah. So what's the total loads we got?
Okay,
here?
so R2 becomes
Uh, 4,333.
4,233.
334.
4334.
4,334.
333.
Okay,
You're down. 333 pounds. I rounded it up, but I should have rounded it down.
Well, that's not.
Oh, whatever, dude. So is R1 1966?
3,600, 7,200.
See, at 300 times what? 300
Right?
Times 9.
times 9
Oh no, it's times
Yeah,
12.
times 12.
What? Yeah.
times 12. 300 times 12 plus 100.
So 7,200. Is that what we have?
2,867 would be R1.
Sure, depending on how you're rounding.
2,866.
Okay?
So
So where is the location of your maximum shear?
R2.
At R2, right? 4,334 pounds or 4,333 pounds, depending on how you're rounding, right?
Yeah.
Okay. So how does our shear diagram look?
Well, it starts at
Fun, right?
Yeah.
2,867.
Okay.
Then you're going down
100 a foot for
then you're going
6 feet.
2,267 over 6 feet,
Yep.
and then you drop another 900 pounds over 3 feet.
Okay, so this changes in.
So the slope will be a little steeper at that point.
Yep, I would agree with you.
Then at that point you drop 2,000 pounds straight down
Okay.
to negative
633? 37?
Okay.
and then
Now what do we do?
another 1,800 pounds over 6 feet.
Okay.
And then drop another 1,000.
Scale got off, sorry.
And then another 900 to end
And we're
at,
gonna drop 900 more.
yep, to end at negative 4,333.
Dude, 933.
What do we miss here?
No.
It's
Nothing.
7, not 3.
What?
Yeah.
My bad.
Oh,
Yeah, I was gonna
That's
say it's
terrible,
not.
right?
Yeah. That's
that's negative 1,500, right? Now that makes more
Do the
sense.
math.
And this is 25? It's still not right.
No, because
What am I doing?
it drops 1,000 there.
This is 6 feet,
Yeah.
sorry. Ugh, goodness. So this is 2433, right? Now you're gonna drop.
To end at
Just-
negative 4,000.
Okay?
So it's 350 for 6 feet, right? Or it's 300.
4334.
300 per foot.
So 900.
Okay, yeah.
I get shear.
Okay? Where do we have shear equal to 0?
9 feet.
At 9 feet, right? not quite to scale.
It's good.
Any other questions on this? On what's expected out of the homework on shear?
No one was abusing.
Okay.
I would have been so mad if I did that at home. Seriously.
How much more time do you need to complete this homework? You have it done by, you have it one more day?
Tomorrow.
Okay. So I put at the end of the day tomorrow? No one's gonna have too much,
No.
no one's gonna be losing sleep tonight? Okay.
But not because of this.
So you'll see that by noon today. I'm not gonna adjust it now, but after lecture we'll adjust it. Okay.
All right.
Okay, in the interest of time, the last thing that we'll look at is section 3.4. We won't look at 3.7. And the idea being that next week we'll start looking at chapter 4. So next chapter 4 we start tying everything together. We look at what do we have to take into account as we're using wood and steel and concrete in thinking about how we're going to design these structures. So how are we going to size up this material? How are we going to take into account typical norms for sizing of materials, things like that. So it may only take us a week, but I do have us a week buffer as well before week 9. Okay, so if we are able to get through chapter 4 all next week, we'll start getting into the concrete portion. Okay, if not, we'll spend week 7 and week 8 working on chapter 4. We'll see how it goes. Chapter 4 is shorter than all of these. We aren't introducing any new types of forces. Okay. Once we're done with today's lecture, we're done with the types of forces that we're going to be working on throughout the semester. So we're not done with the math, but we're done with introducing the types of forces. So so the last thing we need to talk about is the sense of bending in beams. What that means to the structural shape. Okay? And there's a couple of illustrations that your book has, but typically we've been working with some sort of variation of this type, right? We have a point load or we have a uniformly distributed load acting on our beam, right? And all we've been looking at is what are these forces in their magnitude, how are they acting? But we also have to think about what this means to the shape of our beam out in the field. What is it actually going to do? We've talked about deflections, not so much in this class, but in other classes, right? And so what is actually going to happen to this beam? What is it going to do?
Bend.
It's going to bend, right? And it's typically going to do something like this, right? Obviously exaggerated for comedic effect, but it's going to have some sort of concave down or concave up, depending on the types of forces. Are we going to see any change at our reactions? I guess I should say theoretically, are we going to see any change?
Yes.
If we design and construct them properly,
Or
should
no,
we?
because they're going to be equal. Or
It's not necessarily that they're going to be equal, but they're providing the resistance, right? To keep this thing from, because we can control this deflection with how we size the beam. What's the purpose of our reactions?
rotating.
The purpose of our reactions is so that when we load this thing, we now don't have a beam down here, right? We don't have a bridge deck now on the freeway below it, or in the river below it, right? The purpose of our reactions is to hold it in place, okay? So we aren't seeing any deflection of our beam at our reactions. So what would happen to the shape of this beam then if we took these supports and moved them in?
It would bend less.
It would bend less. Where? What do you mean, John?
Like it's just
Between the supports? Do you mean? I agree with you that yes, I believe that you're going to have less deflection. Why do you think you're going to have less deflection in that beam?
because the
Shorter span.
You have a shorter span, right? Does that make sense to everyone? What's going to happen to this segment of the beam though?
They're gonna go up.
Yep, they're going to want to deflect also. Okay, so our shape will actually look like right? Kind of, okay? I do a pretty poor job of accurately drawing deflections of beams as they're loaded, okay?
True.
And sorry, I shouldn't draw here. There's our distributions. Now what happens if we apply a load outside those supports and keep these in place?
Up.
What's that?
It's gonna bend up.
It'll leave it out.
Or, oh, just leave the force in the middle too?
Well, let's consider the case first. Let's apply a load here, and let's apply a load here,
The middle is gonna go up.
okay? Right, something like this? Does everyone agree with that? And finally, what if we apply a load here, here, and here?
Equilibrium.
Distributed evenly.
No bending?
It'll bend,
It will bend?
yes, it'll bend on,
It'll make it M shape,
there you go. Okay.
seagull.
Something like that, right? Okay?
What's a half acre ground?
Does that make sense to everybody, what we're seeing?
Throw that ruler away for this exercise.
What is consistent at the reactions throughout all of these setups?
Yeah.
Dude, this thing breaks.
You have more of my pencils than I do.
Do we have any distortion
They're all somewhere.
right at our reaction?
No.
No.
Not typically, right? What is that going to mean for our shear diagrams? If we're doing shear diagrams, are we ever going to have shear equal to 0 right over these points? What do you think?
Say that again?
No.
Why do you think no? What did we find out from our simple beams? Did we ever have shear equal to 0 right at the beams?
No.
Or right at the reaction, sorry?
No.
Why not?
'Cause
The reactions-
are,
The reaction pushing on.
They always have a magnitude, right?
yeah.
So if they always have a magnitude, there's always going to be shear acting there, okay? So your shear can never equal 0 at a reaction. Okay? So in this section, what they look at is very similar type problems to what we were looking at previously, but we've moved the reactions around, okay?
So they're outside though? They're outside space?
No, so we're gonna move the reactions inside, so they won't be at the beam ends, they won't be at the termination of the beam, okay? The first item that we'll look at is on page 94, example 6. So here we have a beam with a short cantilever section.
It's 4 feet, so.
Say 94. 94. Math 5. One math. That can't be right. Which,
But
that's on 94?
No, page 99.
Oh.
was gonna say, that is not.
I was
Oh,
gonna say, geez.
sorry. I have a poorly drawn 9 on my worksheet here. Sorry, is
There we go.
that better?
Bucking up for an argument there.
Yeah.
And, let me take a look here, I forget if they give us the reactions or if they determine it. They just give us the reactions, right?
Yeah.
Okay,
it
so we
says
know
3,200 on R1.
R1 equals 3,200 and R2 equals 6,400. Okay? So how will our shear diagram look?
We'll start at 3,200.
Okay?
It would go. Oh, that's 720.
Go your 600 pounds down.
What are you doing, John?
He's taking 600 pounds a foot.
Okay, so you're dropping 600 pounds a foot?
No,
What?
7,200.
You're dropping 7,200?
Well, yeah, you're dropping 600 pounds per foot, but a total of 7,200 over 12 feet.
I see what you're saying. You want to take it down to negative 4,000 at 12 feet?
I would like to, yes.
Okay.
Final answer?
Final answer.
32. Okay?
And
What
then
happens after that?
You go up 6,400. So, up to 2,400.
you cheating or something?
No. I don't have the answers. And then down another 2,400.
Right? And this is a, even worse. Poorly drawn straight line, right? Because we have a uniformly distributed load.
It's not bad.
It's acceptable.
It's better than mine.
Why does the book go down to negative 4,800?
Yeah.
Let's check Benny's math here.
Don't check my math.
600 times 12,
600 pounds.
7,200. Tough, man.
7,200.
You're at 3,200 pounds.
and 32.
7,200.
It's 4,000.
Negative 4,000.
Benny, it checks out.
32 and
Thank you.
48, so that's 8,000, because they made a math error,
So it's supposed to-
right? Because how much are you dropping?
7,200.
You're dropping, careful, how much are you dropping per foot? Sorry, I should have
600.
asked a better question.
600.
Dropping 600 pounds per foot, right? Over 12 feet, so what's the total magnitude?
7,200.
7,200, right? So you drop 3,200, and then you drop 4,000. I don't know where they came up with that other 800.
Well, they did it, they put
In the
it,
book?
they
What
divided
are you
it.
talking about?
Oh, and the book is wrong?
Yeah, it says
Yeah.
4,800 pounds.
Yeah, what
They
the
did
hell?
it 600 pounds
That's
Times
twice
12
now the
feet.
book's been wrong.
for
That's like
the
3 times.
What is this?
uniform
But this is supposed
load
to be
and then
for
divided it by point
simplified.
multiplied by the point
So which one do we solve?
Calling us
Half
retards?
Oh, look at, we can make another kind
Scale
of
versus
diagram.
mx equals 12.
That's a moment, though. That's when we're looking at bending. We're talking about the shear diagram.
Their shear diagram drawn the same way.
What are you talking about? See,
Their shear diagram still looks 4,800.
Yeah, they just have a wrong value here. This shouldn't be 4,800,
They don't know how to do math.
right?
I didn't.
Because if you have 4,800 here,
They don't know how to do structure.
your delta is 8,000, right? Everyone
Hell,
in
that
agreement with that?
Right.
And if you divide 8,000 by 12 feet, that's what? 650, I don't know, 658 or something?
666.
666? Yeah,
Hard.
so we definitely don't want to use that, right?
No.
Certainly
Why,
not on-
what's this delta business you're talking about now?
What?
Delta the difference.
So I'm just saying this is delta.
Well, it's 7,200 pounds.
Yeah, if you add
Yes.
800 to it, it's 8,000.
Yes, if you go to 4,000.
Oh,
If
yeah.
you go to 4,800 though,
Oh,
you're
where
saying
they're
that your
putting
delta
their-
is 8,000, which I wouldn't agree with. given the loading condition. Okay?
So the book is wrong, that's the final thing.
Just at that one point.
Just at that one point.
They actually had the rate number on the top.
The shape, yeah, the shape is correct, and they have 2400 correct up here, right?
Yep.
So, yeah, I imagine when the problem was given to the technical writer, the 4000, the 0 was probably written poorly, and the technical writer took it to be 4800, and in the editing process it got missed. Okay? So now we have to look at our bending diagram. And we have to be careful here, right? Because we have two locations where we're crossing. And what have we said in the past? Anytime we go from positive to negative, we have a maximum, right?
Okay.
When we cross from negative to positive here, where are we located on the beam?
Here's a B0.
We're located at the reaction, right? We can't have shear equal to 0 at a reaction. Okay? So we won't have a maximum there. So that means, by process of elimination, this is where our maximum is going to occur. Okay? Can we determine where this distance is?
Yes.
Yes.
How would you like to determine it?
Trust the book.
We can use the rate,
Slope.
yeah, the slope
What slope?
of that triangle.
This triangle?
Yeah.
So 600 pounds per feet? Times x feet? What does it need to equal?
0.
Why does it need to equal 3,200, Steve?
That's your,
That's our initial
That's where it's
magnitude,
going.
right?
that's what
So if our initial magnitude is 600, or
3,200.
3,200, sorry, and we want to figure out where it equals to 0, if we say 600 pounds per feet times x feet equals 3,200, yeah, we'll get a distance
Of 6 feet.
that is this far away where it equals 0. So x equals 3,200 pounds divided by 600 pounds per foot. Okay? So now we know when we're checking, when we're drawing our diagram, where to determine our moment, so we can calculate that maximum. Okay? Does that make sense to everybody? What we're after with regard to this?
So, and that's giving us just the height, like in the picture, the high point. Goddamn.
Say that again.
Determining that gives us the highest point where that'll happen.
On the bending moment diagram?
Yeah.
Yes. Correct. So let's see what this looks like. So at x equals 0, what do we have? No, careful, we're not looking at shear. We're looking at bending, right? Remember, we're looking left to right. At this point, is there anything causing rotation?
No.
So we start at 0, right? What about at x equals 5.33? Okay, so now we are this far along.
Is this like a derivative graph?
If you want to do calculus, yeah, we could.
No.
It's actually integration,
Swear
but
to God.
Oh, no, that's not.
but it
Well
is.
said.
But yes, it is what it is. The bending diagram is the first integration of the shear diagram. Yep. But we're not going to do calculus in this class. So So what's acting at 5.33? Is R1 acting?
Yes.
We're this far away. We're ignoring everything to the right. Or we're taking account everything to the left.
Plus 32 minus
3,200 plus the 5.33 times 600.
Remember, we're working in a moment, so what do we have to do with the reaction? We have to multiply it by a distance, right?
Yeah, so
Okay? What do we need to do with our uniformly distributed load?
add it.
What's that?
Add it. Times it. I don't know.
Turn to your point load.
Turn it to a point load. So it's 600 pounds per feet times, work. 600 pounds per feet times 5.33 feet, right? How far away is it? 5.33 divided by 2? Yeah, 2.67. Now, are both of these forces opposite? Or are both of these positive? Sorry. Not that I didn't do any foreshadowing. Think about this point.
No, they're opposite.
As we grab onto this point, what is R1 trying to do? Is it trying to rotate this way?
Yep.
Okay, so R1 is going to be positive, right? What about this force? 600 pounds per feet. When we resolve it into its point load, and it's acting down, is it trying to rotate this way? Or is it trying to rotate this way? What's that?
Regards to R1, positive.
Positive to
But we're
R1.
not looking at R1. We're looking at a point 5.33 feet away.
Okay, now I get you. Now it's negative.
Now it's going to be negative because it's going to be trying to rotate this way, right? Okay? So this guy's negative. So R1 has a value of 3,200 times 5.33. So it's 16,000 and about 1,100, I think. Sorry. And what does this guy end up being? That's about 3,000 times 2, so I'm gonna calculate. Unless somebody else has punched it into a calculator.
Tried to without getting a damn error.
$8,538. Okay, so my 17,100 is an approximation there. Well, we can figure this out. This is 7,171 is in the ballpark. Okay?